So, after you have completed this edge detection on an image, we said that the next step is to identify lines. Okay. We are particularly interested in lines in the context of automotive applications, because we expect that most roads are like straight roads. Of course, there are bends, and particularly when you are moving over a small hill or a mountain, you go around taking bends, right. Bends are there, but by and large what is important is that you have to detect these lines. Okay. And our hypothetical example was also about the fact that there is a road, and then there is a left edge, there is a right edge, there is a divider in the middle, and then there is a lane marking, right. All these we had assumed. You may argue that edge detection with canny edge detection particularly would be sufficient if you are just looking at straight lines. Okay. Canny edge is essentially for edge detection. If your edge happens to be a straight edge, it will simply detect that as a straight edge, but it will not call it like a line. It will not declare anything as a line, it continues to call it as an edge. It is just that we interpret it as a line. Okay. Therefore, you cannot assume, and perhaps these are some small mistakes that people may end up doing, that they may say, okay, let me restrict this example to just try canny edge because we are only looking at straight lines. That is a limiting way, because as I said, the road can also turn left, can turn right, and so on, and then edge canny edge will only give you that edge. It will not do anything whether this edge is straight or whether it is curved or whatever, it does not say anything. Therefore, Huff-line transform is the next logical thing to do. Now, this Huff-line transform is a very see, there are so much of literature out on the internet that you could pick any literature that you are comfortable with. Okay. So, however, in this course I would strongly suggest that you concentrate, understand either canny edge or Huff-line from OpenCV perspective, so that it becomes easy for you when you are working on tools like MATLAB and so on, right, or Python, or Python, particularly Python or C, any of them. OpenCV is an important library API for most image processing applications. So, you should look at definitions around that. So, I have tried to sort of look at a mix of several literature that is available, and then I have tried to make a very small module on Huff-line, because I do not want to repeat all the good material which is out there on the out on the web. Alright. So, how do you detect lines? Go back to high school, go back to the famous straight line equation. You have x here, you have y here, and you are interested in knowing the set of points starting from xy to yi to xj comma yj. I have just shown 2, but there are infinite number of points as you go along here, right. As you go along here, there are infinite number of points. Let me just take another color, so that so many points out there, which essentially I do not want to blur it, because blurring is another algorithm step, but just to tell you that there are many infinite number of points. If you are able to show that they all are on the same sort of, they are all aligned, these are all aligned points, then it must be a straight line. That is all you have to say. Okay. So, this A and B, as you know, is essentially gives you information about the eye inclination. So, there are lots of combinations for xy in order to arrive at this notion of aligned points. Now, this intuition is outstanding really. You should spend time to understand Huff-line from this picture. It is a nice picture. See what has actually happened. Here you have done a transform, as you see the word here, Huff-line transform. What is the transform you are doing? You are transforming from this xy plane to the AB plane, okay. And on the AB plane you find that this AB intersection is the most interesting part. If these lines, these points xi, yi, xj, yj and so many other points, all of them are aligned in the same line, all of them will come to the same intersection point, that is the key here. So if you start counting the number of times these lines are intersecting, you actually know the number of points which actually make up the line, that is the interesting part. And again I urge you to look up several places on the internet where this material is discussed extremely well. So I do not want to put too much emphasis there. So that is the most interesting part. Now how do you actually realize all of that? Well, take the straight line into the polar coordinates, take it into polar coordinates where everything coordinates, where everything is represented as rho and theta, right. And you know this famous equation, rho is equal to x cos theta plus y sin theta, every point holds this equation, every point, this is the key here, every point holds this equation. You know what you do is something even more interesting, you essentially do the following. Supposing okay, let me put it this way, in general for each point x naught y naught, okay, we can define a family, we can define a family of lines, okay, go through that point as, what will you do, rho, I will just say rho theta x naught cos theta plus y naught sin theta, okay. Meaning that each pair of rho theta theta, let us say rho theta theta, that is rho theta pair. So this is actually rho theta, that is right, that is for a rho theta, but for this rho theta pair, okay, each pair of rho theta, for each pair of this rho theta, it represents, each line passes through x naught y naught, okay, meaning that each pair rho theta represents each line that passes by x naught y naught. Now if you plot, okay, if we plot the lines for a given x naught y naught, if we start plotting the family of lines that go through it, what we get is a nice sinusoid, okay, we get something like this. Sorry, I should not put this kick here, you get something like this, okay. This is essentially theta and this is essentially rho, you start getting this, okay, we get a sinusoid. For instance, you start putting numbers, x naught you put 8, y naught you put 6, you get a plot in the r theta plane, plot 1 call it. Then what you do, you essentially see, you have to note that always rho is greater than 0, that is important, and theta is lying between 0 and 2 pi, rho is greater than 0, can be 0, and this lies between 0 and 2 pi, okay, theta lies between that. Now what you do, you go on giving values for different values of x naught and y naught, then you will start getting a family of curves, okay. All of them will be intersecting somewhere or the other. Okay, let me just complete this. Okay, you take one more and intersect it here, goes like this, and just to keep it away a bit, and one more goes like this. So, you see you will go on getting these 3 plots which intersect at one point. Okay, there is one intersection point here. These coordinates are the parameters for some rho theta or the line which has these 3 points x naught y naught comma x1 y1 and x2 y2. Okay. All of them are intersecting here, which means they are in a line, that is all you are saying. So, that is the point about detecting Hough lines in actual implementation. You can actually do this. In general, you can say a line can be detected. Let me summarize this whole discussion. In general, you can say that a line can be detected, by finding the number of, what is it now? It is a count, number of intersections between curves. Okay. So, it is a very nice way to find out the line and how you can detect this line. So, essentially you are creating a nice table of all theta and rho values, and then you know whichever has the highest count. Essentially finding the number of intersections means the count. Every time there is an intersection you can increase the count by 1, and then you know how many points essentially form the line. So, essentially that is what you are saying. The more curves intersecting means the line represented by the intersection have more points, simple. So, I will just put it here, more curves intersecting, more curves intersecting means implies line represented by that intersection have more points. What a nice intuition indeed, right? And this is what the Hough line is all about. So, I will just summarize. You can make a nice table. Okay. You can have 0 here for theta, this can go to theta max, this can go to theta min. Okay. You can have rho min here and rho max here, then keep filling this table. That is all you need to do. Okay, this dot line I should remove. Very simple to see the count. Supposing this has the maximum count, this actually shows one count. That means all points, okay, which you have chosen x naught, y naught, x1, y1, x2, y2, x3 and so on, all of them form one line. This is one line, that is all. Okay. So, these two put together, the canny edge detection in canny edge detection in image processing using a camera sensor and the Huffline transform post edge detection form the most important part of our further demonstrations and your own tests and trials that you can do part of this module. So, our basic infrastructure for following a lane includes a robotic platform. It is a Kobuki robotic platform. It is from a company called Eugene Robo, and on top of that is our basic autonomous vehicle. This is our vehicle, and of course it has several wheel sensors and all of them, wheels here, and then you have to apply thrust on these wheels, and essentially we are going back to our basic Breitenberg algorithm, where the sensor is indeed the camera and the actuator indeed are these two are the motors to which are coupled these two wheels, right. So, it is the same model. So, we are taking a very simple model and trying to show you what are the things that how complicated even a simple model can actually result in. So, this is our basic camera, and this camera is a USB camera to which is connected this you can see that here there is a small single board computer which essentially is a Raspberry Pi platform, and then there is a battery bank and all of that. So, this essentially forms our autonomous vehicle, and now let us get into the details of the steps involved in showing you a demonstration. Before going to the demonstration, you must know the platform, you should know the steps, and then you should actually see the demonstration, right. So, we will go to do a code walkthrough and show you what are the major steps involved in the process. Okay. Now, what is important is if you are using camera as a sensor, you must do what is known as camera calibration. Now, camera calibration essentially means that a board like this is a marker, okay. This marker should be used to take care of several distortions that a camera can essentially inherently have, okay. So, this is very important. Why does the camera have inherent distortions? Because you are talking about an optical system, there is a lens there, the lens introduces distortions and those distortions have to be corrected, and there are steps which you have to follow before you actually start using the sensor. Now, I can tell you one big mistake that most people do, you do not start a calibration like this, right. This is already going to introduce distortion for you. You are expected to mount this rigidly on some sort of a cardboard. I have just taken this to show you, put it on a rigid cardboard so that this sheet itself is rigidly held, and then you start your calibration process, okay. So, this is the first step. So, remember in IoT you are bound to have sensors, and if you are going to have these sensors, if it is air quality you are going to have air quality sensors, if it is going to be autonomous driving you are going to have lidars, radars, camera sensors and so on. Any application you take will have sensors. First step is to calibrate those sensors, particularly if you are using this kind of camera sensors. They say some data sheets talk about this kind of calibration is something very high end cameras perhaps may not need it because they will already do a few things and make it sophisticated for you, but if you are buying you know your own lab based equipment and lab based simple camera sensors, the calibration process is available, and so you have to go through those steps. And let me also assure you that very nice algorithms that are proposed for camera calibration, all of it will be available to you in terms of a nice function call in OpenCV which you can directly use, but you should know what those functions are and what is the what is the function of the function, right. So you must know what exactly is happening so that you will be able to appreciate this whole process of calibration, right. So let us get into the details of this whole process and also do a code walkthrough, and then we will actually see a demonstration. The first step towards camera calibration, when you want to do code walkthrough through the whole step, as I said, is trying to establish the camera calibration. Let us see what is the code corresponding to camera calibration. So let us now quickly do find out all, I mean look at the source code of all that we said. First of all, what is your objective? Your objective is to use some kind of a reference chessboard or a checkerboard and then try to calibrate the camera. Most often this camera calibration is something that is done for pinhole type of cameras. Larger professional cameras which are used in perhaps in autonomous driving will also have something equivalent, but you may not have to do this kind of very elaborate process. But for most lab experiments and all that, this is the first step for any optical device that one uses, because lenses will bring in distortion. So idea is that these are the points, the intersection points that you see here, 1, 2, 3, 4, 5, 6, 7. There are 7 intersection points, and this can be easily translated into this picture that I have drawn here. Okay. So let us focus on this picture here. Let us focus on this picture here. You can see that these are the intersection points. These are essentially, these intersection points should lie exactly sort of red dots which you assign to on top of the basic chessboard that you have. And once this chessboard is twisted, is radially distorted, it should be able to continue to track it and know how much distortion has been applied on this. So let me give you a demonstration. Okay. So let me go back to this physical chessboard that we have here. Okay. Now you have these red dots on each one of these points here. Okay. Here, 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 all these red dots are there, and for some reason the image it sees is like this. Okay. That means how much is the distortion it should know. So that information, because now this 2D in a way becomes, if you do like this or if you do like this, becomes 3D, right, there is depth immediately. So somehow you should be able to look at this 2D image and also look at how to convert this into something equivalent in terms of 3D object points. All of that is done in the OpenCV. So let me again point you back to this steps that I have. The image points are these cross section points, are these red dots I mentioned, are essentially the 2D points. From that you will be creating these object points, which essentially comes because of tilt in the chessboard, which will give you the depth information, which will become 3D, right. All of this essentially leads to sort of estimating the distortion coefficients and the camera matrix of interest. Okay. That these two, once you have estimated through the process of camera calibration, you feed that information to this function called cv.undistort. So if you do that, you will get an image which is completely undistorted. Okay. So essentially is I have sort of glossed over the whole process because it involves a lot of intricate linear algebra background, but the point really is that you will need to estimate these two. I have put it here, you need to estimate the distortion coefficients and the camera matrix. Essentially you have to, let me show you this picture again, chessboard, red dots at these intersection points, depth information that is available, keep tracking the depth information, correct the image for this depth that comes, and essentially keep ensuring that the camera knows how much of distortion how much of distortion is there, because it has estimated the camera distortion coefficients, has the camera matrix with it, applies this correction using this function I mentioned to you, and you ultimately end up with an undistorted image. Okay. Let us now look at the source code of that and then move on to the remaining parts of the program, which essentially did the straight line, a turn to the right, and then a turn to the left. Okay. So, let us do that. See, take this image, okay, take one snapshot of this image, take one more snapshot, take one more like this, take one more like this, collect as many samples as possible, collect about let us say 25 or even 50 images. The large number of samples that you take, because you are trying to estimate the distortion coefficient, is not it, and also you are trying to come up with the camera matrix. So, therefore, as many pictures as possible if you collect, it is always good. So, take all those images, those little images that you have in the process of trying to estimate the two things that I mentioned to you. One is the image points, essentially those red dots which are exactly at the intersection, and from that you are trying to get to the 3D, which essentially is nothing but the image points, because you will be rotating it. So, let me show you the code that does exactly this. Essentially this is saying that you have 7 cross 3 intersection points, those red dots are 6 on the x axis and 7 on the y axis, essentially that is the number of points that you have. So, and that is one thing. The second thing is the object points that we mentioned to you, I mentioned to you, is indeed in the 3D point cloud space. The image points are essentially 2D points. This part of the routine where the mouse pointer you can see is essentially reading one image after the other, right. It has to read all these images and then take each image at a time and then identify the you call this function called CV find chessboard corners, and it is trying to estimate all the corners for each of the images. Essentially you will end up with both the object points as well as the image points as and when you run it across all these images. At the end you will end up with as you can see, we have done a print of object points and image points. So, how many, if you have 25 images that you have taken, how many object points will you have? You will have one set for each image. You see you will get, if it is a 6 cross 3, so it will be a 6 cross 3 6 cross 7 in our case, you will get the object image points and image points and object points for every frame. This is like one frame, right, with one image that you have captured. If you turn it, if you turn the picture, you will get one more snapshot image. For that snapshot image you will get object points and image points, like that you will keep getting for all 25 or 50 or any number of images that you have taken for the purposes of calibration. What you do with all these points when you come to this code here, OpenCV function called cv.calibrate, to which you will pass the object points, the image points, and also the size that you are considered, which is essentially 6 cross 7 in our case, and then you are trying to estimate what is known as a camera matrix and the distortion matrix apart from the radial vector, which is rvex, and also the tangent vector, which is the other parameter. For the moment we are not looked at radial vectors and tangent vectors, we are only interested in the camera matrix and the distortion coefficients. Now what you do? You take this camera matrix, you can see this function cv.undistort, you take the camera matrix, take the distortion coefficients, take one of the images that you have of interest and then feed it to this function. What you get at the output is a completely undistorted output, which is essentially this variable here, which is DST. With this you have done the camera calibration. Okay, so let us see how to put everything together in terms of a small demonstration. My project staff Vinod Hegde has worked extensively on this, trying to make a small system working for you. Let us see how exciting this whole set of algorithms get into a nice process of demonstration. Remember, I mentioned to you about camera calibration. This is not the way to calibrate. Put it on a hard surface and then do the calibration. So, just for holding this in my hand I am just showing you, but this is not the way to do it. Put it on a rigid surface so that it is straight, and the idea is you should be able to detect all these cross sections and then map it back onto the complete camera squares, right, and then you are ready to go, good to go with as far as the calibration is concerned. That is just the first step. Then a lot of matrix operations have to be performed before you actually put in the required coefficients and then conclude that the camera is correctly calibrated. Let us think about that as a very first step. After that, you will actually start the demonstration. We will have to actually start looking at how to mount such a camera and ensure that it is does this line following, and even if the line is not straight, but it is turning to the left and right, it should be able to do all the algorithms that we discussed. For that, let us now slowly zoom the camera towards the setup here. Okay. The setup here comprises of what? So, let us sit down slowly and see what are all the things before we actually start a demonstration. The setup here comprises of a camera. This is all the power bank, this is an onboard computer, and this is the robotic platform that is like equivalent of our autonomous vehicle that we had proposed in this module. Now, look at this. This is a straight line, this is another straight line. As far as camera is concerned, this is also a straight line, but orthogonal to these two lines, right. So, and these are all small lines that the camera is catching. So, canny edge has to be clever enough to take those which are dominant and then start only capturing those important lines of interest. So, any image captured by such a camera first has to be converted to grayscale, then you do what is known as a Gaussian blurring, and then you apply the canny edge algorithm. Number of edges, number of lines are indicated soon after you perform the Hough line. So, the moment Hough line is done, number of lines are indicated in this view of the camera. Particularly, you can see we have turned the camera such that it is just pointing to a very small area. Here what you should also do is set your thresholds right, just to identify the most two dominant lines. Okay. And what is also important is the region of interest. The region of interest, since the camera is pointing down here, is like a sort of a triangle here, and this because of the calibration and conversion to grayscale in the initial stage, it is able to identify these two lines, dominant lines, okay, and then start following these two lines. So, I may have left things unanswered for you, right. If your region of interest is within this, you have to identify these two dominant lines. What does it mean in terms of actually implementing an algorithm? It simply means that you have to calculate slopes, okay, and the effort in making this robotic platform move based on the region of interest is essentially trying to understand the slopes of these lines. This will have a certain slope, this will have another slope, these two will have different slopes. You can identify the thickness, for instance, as an important feature, and then look at the thickness of these lines and take this line, this edge separated by this edge and that edge at a certain distance, and then say these are the two lines of interest. So, it can be a very interesting algorithm even to identify the two dominant lines, edges in a given region of interest. So, I let you imagine how we would have actually taken care of the millions of lines, straight lines that are coming in this region of interest, and just picking these two dominant lines, right. So, that is one part, but at the same time you also have to note that one trick to do that is to look at slopes, as I mentioned to you, and then see if you take a straight line like this of this thickness, which has one edge, second edge, third edge and fourth edge, and you take the slopes of both of them and add the two slopes, you end up seeing that the slopes cancel each other 1, 2, 3, 4. Those 4 dominant edges which cancel out the slopes indeed are the two lines of left edge and the right edge of interest. Okay. So, that is essentially what would happen. Then let me, that is essentially what we have done in this demonstration. Let us see this paper, which essentially is the crux of the demonstration. What is the starting point? You have coordinate 0 0 here, assume that this is the start. You have two straight lines, right. This is the straight path in which the system has to move, and that is indeed the start. Start is indicated here, you can see here, this is the start. This is the lane of interest that it has to move. Then the Kubuki, the platform comes to this point here, comes to A. What would happen at A? At A, it has to take a right turn, isn't it? It has to take a right turn. You will see that the left edge will have a negative slope, the right edge will have a positive slope, and together when you sum them up, you will get a number which is less than -6. If you get a number less than -6, the sensor output simply gives thrust to the wheels of the platform to make a right turn, which means this threshold adjustment becomes very critical. The threshold is essentially from -6 to +6. If you get the sum of the left and the right slopes less than -6, you have to take a right turn. The same thing will happen when it comes to B. It will again continuously, it will be calculating the slopes, all across it will be calculating the slopes. At B, it realizes that the slope is more positive compared to what it was at A, the right edge. I mean, the right edge is more positive compared to A, and the left edge is less negative compared to what it saw at A. With this, you will find that the sum of the left and the right slope is greater than 6, and moment that happens, the sensor signals to the thrust motors to take a left turn, and then it makes a left and then proceeds straight. So, if the two slopes cancel each other, what you should do? You should simply go straight. This is the simplest possible algorithm that we can look at. Okay. So, now let us turn our attention, with this background, let us turn our attention to the actual demonstration of all that we have put together. So, you can see now that the autonomous system is moving forward, the region of interest is captured by the camera, the slopes are cancelling out each other, it has started, it has now come to position A. At A, what should happen? The sum of slope is less than -6, the thrust is given to the motor, it takes a nice right turn and tries to move forward, and again sees two straight edges, 4 edges. Each time the 4 edges, the slopes are cancelling out continuously, and therefore decides to move along the straight line, and you can see a slight adjustment. It is trying to find the two lines and then tries to make a correction perhaps again, and let us see what it would do. You can see that it is making its way, trying to correct itself away from the two lines. Here it comes to position B. At B, it has to take a left turn, and because the sum of slopes is greater than 6, it takes a left turn, and then it sees the two lines and starts moving forward. It will do something interesting at the end, which is I am sure will be quite puzzling for you. You can see how the algorithm, while we have put all these high performance algorithms in place, if the two edges, one of the edge actually misses, it starts identifying some two dominant edges in the region of interest that we have defined, and starts following those two edges thinking that indeed that there is a straight line. You will see now that you will see it has gone okay till now, and now it starts drifting. There are no lines. Some two imaginative lines it has found from the floor, because the floor tiles have indicated it some two lines. It is doing the same calculation. It has found some slope differences. It has taken a right turn and it is moving forward, and then perhaps it finds during its continuous calculation finds that there is a difference in slope. Based on that, it would either take a left turn or a right turn and so on. So, it becomes quite unpredictable now, and perhaps these are the dangers of all these algorithms if you do not design them in a perfect manner. So, you may have to bring in fail safe options, you may have to bring in options of halting the vehicle in case there is a mismatch and so on and so forth.